Hello, so I wanted to take this example to help you figure out how to find gravitational potential energy, okay? This is the energy stored in a gravity field when you lift something, all right? So, let's see here. Let's just review what you got so far. Springs, I'll say elastic materials, okay? So, for elastic materials, when you pull on them, different amounts, the force required changes, all right? So, energy stored is going to be 1/2 Fx, right? And since this slope is called the spring constant, if you plug in Kx for F, because K times the equation on the line, the equation is going to be F equals Kx, right? So the height of this triangle here, is simply Kx, right? So this value is Kx. So this becomes 1/2 Kx times x, or Kx squared, right? Now, let's contrast that with the idea of work. Work is energy transferring into a system due to an external, that means outside the system, external force. It's due to an object outside the system. So external force due to an object outside system. So we simplify this situation and we say that the force exerted is constant. So the external force we're talking about here, we're saying it isn't changing. So the graph looks like this, and the object is moving x distance, and over a time period, after the object moves a certain distance, we would have a rectangle here, right? We're also saying that F and the distance the object moves are in the same direction, all right? And this means that if you just multiply F times x, that gives you the work or energy transferred into the system, okay? Now, we're going to use this idea here, okay? And we're going to figure out an equation for gravitational potential energy. Please consider an object that is pretty close to the ground. Doesn't really matter, but it's on the ground. And then at some moment in time later, who cares how it got there? But some strong man has then lifted the object above his head. Okay? Whoops. He's got antlers. Let me try that again. So, maybe I'll start by doing this part first. There we go. Okay. So, there's our strong man who lifted the block. Some height, some change in height. All right, change in h, meaning change in height. Our system can't just be the block okay? If it were just a block isolated in space somewhere, there'd be no way to store gravitational potential energy. So we're going to need to say block, and the block has to be in some gravity field, which is part of our system. So block plus gravitational field. I'm going to write gravity field for short. Okay? And this is at, I'm going to make the ground my zero gravitational energy. Reference line. I'm going to say the block is not moving. There's nothing elastic in our system. And this is the same. We're saying E gravitational equals 0 at that blue line. So, question. If the system is our block gravity field, the block and our gravity field is our system, is there a force acting on our system from outside our system? What do you think? Is there anything exerting force on our system between the moment in time on the left and the moment in time on the right? Is there anything exerting force on our system? Yeah, the person had to lift it, right? So, since the person had to lift our system, he's doing work on the block energy system. And if you'll recall, the way we calculate work, right? Let me add a slide, and I'll go over that really quick again. No, that was my first slide. So if you'll recall, we calculated work by multiplying the force that's required to lift the object, or move the object, times the distance it moves, okay? So, going back to our slide, we know the distance the object moves. It moved up delta H, right? Its change in height was whatever delta H is, okay? We don't know the force the person exerts. So let me help you with that part. For an object of mass m, how much force is required to lift it? Consider the simplest case. Lifting an object with constant velocity. Now, I'm not talking about when the object's at rest and then it starts moving. We're going to forget about those moments in time. And as the person lifts the object, we're not going to talk about the moment in time when the object slows down, okay? We're only talking about the time period when the velocity is constant. So let me go back here and say, assume that while energy is transferring, okay, the velocity up is not changing or constant. This makes a lot of things easier, okay? So while the work is being done, and these moments in time here, that time interval, we're saying velocity isn't changing, right? So, and when you lift an object with constant velocity, what's the force diagram look like? The weight down has to equal what? Force due to person lifting. And I don't know, way back last semester, you figured out a graph of weight versus mass. You basically hung masses on a force sensor. And you found that on Earth, the weight of an object is equal to, I'll give you the exact number, 9.8 newtons per kilogram times m, right? And we approximate this. We call this a gravity field of the Earth, the strength of the gravity field. And we approximate this as weight is about equal to 10 newtons per kilogram times mass, right? So if you know an object's mass, you can multiply by m to find the weight. We don't usually call this, we don't usually write the number like this. We usually write it like this, though. We say weight equals mass. Let me say it this way, sorry. This number right here, we're calling this g, okay? Lowercase g. It's the same as the acceleration due to gravity. The units, newtons per kilogram, are actually, you could convert those units to meters per second squared. So this lowercase g means acceleration due to gravity, or it means gravity field strength of the Earth. And those numbers are the same because the strength of the Earth's gravity field determines the acceleration due to gravity, okay? So I'm just going to write weight is equal to mg here. Are you guys good? Now, that means the force due to the person lifting is also equal in strength or magnitude to mg, right? So now we got everything we need. If I go back to the very first slide, we know that the work done is going to be mg when you lift something with constant velocity times the distance you lift it. So, in other words, so work, we got any elastic in the beginning? No. Any EK in the beginning? No. Any EG in the beginning? No. But in the end, we somehow magically have energy stored in our gravity field, right? Well, how does it get there? Energy was put in when you lifted the object because you exerted force on your system and the object moved in the direction you exerted force. So, work, energy put into the system, goes into gravitational. So, the energy put into the system gets stored in the gravity field. That's what this is saying. And the energy stored in the system, the energy transferred to the system is going to be force times how far it moved, right? Well, when you lift something constant velocity, the force is going to be mg, right? That's the weight of an object. And the weight has to equal the force you lift with if the velocity is constant. And the height that you lift it is called h, or I'm going to call it delta h, which means change in height. And that's going to be equal to Eg. So out of our definition of work comes our definition of gravitational potential energy. It's the mass times the 10 newtons per kilogram times the change in height when you lifted the object. So anyway, hope you liked it, and that's how you find gravitational potential energy of a system that you lift. Thanks for watching.